Here it is. So you are asking this exercise, right? To show that each string derived from a context-free grammar by a leftmost derivation can also be derived by a rightmost derivation. So we said that, well, perhaps a formal demonstration was not, well, it is possible, of course, but that you were not required to do it so formally. Yeah, if you can do it, of course, it's better. But let me show you what does it mean to have a leftmost derivation and what does it mean to have a rightmost derivation, okay? For this, I'll draw again this, oh my God. Okay, so now you are seeing my screen. So I'll try to parse again this famous string. This is the Zaza string, which I told you it was going to be famous and we better be friend with it. So let me write the grammar down here again. Perhaps you know it by heart now. M, it's A, M, A, and N is B and B. And M goes to Z, and N goes to Z as well. Okay. So in order to parse this string, there are two different strategies. One of these means or has to do with the direction we are going to analyze this string. So if we start from the left, we will see that we need to skip this Z because we cannot do anything with this. Why? Because it will correspond to this Z below in the grammar, okay? So then we recognize an A, and we have an A here. So there is a hint that we need an M between the A's. How to get an M? Well, it's relatively easy. We can see that with this Z, we can just change into Z, and then we will have an M. Okay, remember we are analyzing from left to right. So now that we can convert this symbol, we have here AMA, which if we analyze this string, we can convert AMA to M. So we will do that. Okay, now we have ZM, which looks very similar to this one. And then we need an N here. How to get an N? Well, we need, again, to substitute this before an N. And then we know we have BNB, like Airbnb. Oh, I think I want to go traveling, right? But no, we have BNB, sorry, bad joke. And we have an N here, okay? And now you can see we have Z, M, N, Z. At the end, we will have something like this, Z, M, N, Z, and then we have the root here, S. And I have drawn this on purpose like this because this way it looks like a tree. That's why these are called syntactic trees. This is the root, and these are the leaves. Yes? Hojas y raíz, root. Okay, so several times we will see this upside down, starting from S at the top and the leaves are at the bottom. So it's the same, just is the procedure if we want to generate. This way says generate. And this way is to recognize. Recognize what? String. If we can recognize this string, means that we can get to S. Then it means this language or this grammar recognizes this string. Otherwise, the string will not be recognized by the grammar. It does not belong to the language defined by this grammar. Yes? When we talk about generate or generation, we are talking that we start from S, and by following the rules from this grammar, we will obtain a string. So most of the times it will be the same grammar, just if we are converting from this to this or the reverse. Okay, now I want you to notice something that we did at the beginning. We started by oh my God, what's that? Sorry, we started by working with this side before. Yes, you remember? So it means we are starting with the leftmost derivation. That's what it means, the leftmost derivation. If we started with the rightmost derivation, then we would have started with the right part. So this would be a rightmost derivation. As you can see, for recognizing if this string takes us to S or not, it doesn't matter. We can begin from the left or we can begin from the right, and at the end we will obtain exactly the same. Yes, so this is a leftmost derivation starting with these changes, and this is a rightmost derivation. Let me write in little, just a smaller version of this so that you can get more convinced that is exactly the same. If we start again with Zazla, and if we start from the right, then we will see that we can begin working with this V. This will be N, and then we have Z and Z, yes, and this will be N. And then we will continue working with this, and this will be M, and then we will have A, M, A, and this will be M. And let me move this. And now we can finish just by doing Z, M, N, Z, and this will be S. So at the end, you can see it's exactly the same tree. The red one is the same as the blue tree. But on its construction, we started from right, and for this one, we started from the left. So this is the difference between leftmost derivation and this is rightmost derivation. And there is a third way of deriving, which can be central derivation. In this case, there is no central derivation because we have only left and right symbols. But just imagine we have something like S and A, B, C, for example. Then you can choose which one you want to obtain first. A, which will be leftmost derivation, C, rightmost derivation, or B, which would be central derivation, right? So usually central derivation is not so called as that because usually you don't have three elements to start with. It's much more easier to have leftmost or rightmost. Another element or another issue is that if you have a grammar that has something like this, XM, then it would be exactly the same to derive from the left than to derive from the right? Because there is only one symbol to start with. In this case, it would be the same. So the exercise asked you to demonstrate that whenever you have a leftmost derivation, it would be exactly the same to do a rightmost derivation. You can work this by using an example like now, which is not a demonstration, but at least I wanted you to grasp or to have a sensation of how, or a feeling on how to work with leftmost and rightmost derivation. The other issue we have, and I think it has to do with the second part of the homework, has to do with this, which is an ambiguous grammar. What do we mean by ambiguous? Please do not confuse the fact that a derivation can be leftmost or rightmost with ambiguity. This is not ambiguity. Why it is not ambiguity? Because at it doesn't matter if we from the left, from the right, we obtain the same tree. In this case, this is the same tree. So same tree, same tree. Whenever we have the same tree, there is no ambiguity. However, if for a single string we have more than one syntax tree, then we will see that we have ambiguity. And I am sensing some telepathic questions from you that say, Professor, I see that you draw this below, so I think this is not exactly the same tree. Well, perhaps my bad because I draw this below, but if you align this to the upper part, you can see it's exactly the same tree. So please do not get confused by this. Okay, so is this clear? Okay, so this is not an ambiguous grammar. Why? Because for a single string, there is only one possible syntax tree. It doesn't matter if we process from the left or if we process from the right, the syntax tree is the same. Now, let's work with the other string in homework, which it was, sorry for changing too much, is ICTS, ICTSES, S. Let me see if I can remember it correctly. Then sentence, else sentence, or if condition, then sentence, or what? Or just, okay, or just S, sentence. And the homework, sorry, please close your eyes so you don't get dizzy. So now the homework, it was, I'm trying to see, this is ik says. So probably, I don't know if the exercise says it. Let me open my book so that I'm not changing so violently the screen, because otherwise it's more difficult for you and for me as well. So it's page 99, right? Okay, it says, yes. Iktik, iktik TS. Okay, so this was the homework, yes? So if we try to parse this string, we have different versions, we have different possibilities. Let's explore them. Let me write this as before. And we have two patterns here we can obtain for S. Remember that at the end, we want to obtain S. So the first one, with the first three elements, we do have them, ICT, ICT. Then the second one, we have again here, ICT. And perhaps we have ICT SES. So this is one way of parsing it. Let me use colors again so that we can see the other way of parsing it. Yeah, ICT, ICT, SES. So I'm in class, so this is number one priority. No one can interrupt me. Okay, so if we color this, we can see again that if we convert this part ICTS ES, okay, I think I need to, I cannot do it with colors. Let me just do the conversion of the symbols. So we have here ICTSES. So we have ICTS like this. We need to convert this to S by using this last rule. This is S. And now we have ICTS. Oh my God. ICTS. And this is S in turn. I'm using this rule. And then we have ICTS ES. C, T, S, E, and we need to convert this to S, to uppercase S again. And finally, this is an S. Yes, sorry for my horrible lines, but I think you understand anyway, right? Okay, so as we saw, we are taking this as an ICTS, as an S, and then this else belongs to this part. Yes. So maybe colors are not helping that much, but I cannot erase anymore. To make it clear, now let me parse the second one. Now we will do this ICTS, CT, we need to convert this to S before doing this. And also we need to convert this to S as well. Now we will do ICTS, ES, and this will be S. And finally, we will do ICTS, and this will be S. Yes, so perhaps now I can choose the colors properly. Good. So in this case, this is an inner if condition then sentence. And then we have here, if condition then this, else sentence. And in this other case, we have this as a sub-sentence, and then we have this independently. I don't know if you are getting it. I think you were, I don't know, it says, it doesn't, yeah, it says it's if condition then sentence. If condition then do something, else do something. So this S can be in turn another conditional sentence, right? In the first case, we are doing something. If this condition is true, then do this. If this condition is not true, then do this. But in this case, we are saying if this condition is true, then do this. And in turn, this will evaluate another condition. And this will try to evaluate if this condition is true, then do this. And if not, do this. So perhaps this can be disambiguated. And I think this will be much more clear to you if we use parentheses or curly braces. So let me write both. And I think by this way, it will be much, much clearer. So the first one says, if condition, then if condition, then do this, else do this. This is the first one. And the second one says, if condition, sorry, I forgot condition here. If condition, then if condition, then do sentence, else do sentence. Let me see if it's not the same as before. Condition. I think I did the same, right?
Looks similar.
Yes, yes. So I'm doing something wrong here. Let me check. Let me try to disambiguate by using curly braces. I'm doing something. Let me try to find what it is. Else. Or perhaps it cannot be disambiguated even by using curly braces. Also, we need to see if semantically it has some effect or not. Mm. So I know you are a very good programmer, so if you can help me solve this, and also you have solved your homework, so you already know how to solve this. So if you have an idea regarding this, maybe it's not possible to disambiguate this by using curly braces. Maybe, but let me think. And please, you think as well. Because it is different. It's different because the second one, this will be executed if this condition is not true. And the first one, this will be executed if the first condition is not true. So it should be different semantically for the processor. So I think that should be, we should be able to express this with curly braces. Like in this case, condition, then do this. Uh-huh. Open, close, then else. Mhm. Okay, now I think it's solved. In this case, this brace, which correspond to if, is closed here because we have if condition, then inside. Then we close this curly brace. And then we have else corresponding to this one. Then we will have this other sentence here. This means that this will be executed if this condition is not met. And the second one corresponding to this structure, we have if condition, then and you can see this curly brace is closed here. So in the first case, it is closed here, this, and in the second one, it is closed here. Okay, so now I think this is much more clear. And we have this, which corresponds to the second part. And in this case, it corresponds to this part. And now with the corresponding colors, I think it's much more clearer, right? Okay, so semantically, there are different these two. The problem is that this grammar does not allow us to differentiate between one meaning and the other meaning. We need something else, which are the curly braces. If sometimes you wonder why do we need so many curly braces in C, or sometimes we need them on Python. In Python, you will use indentation. I don't like it, but well, that's the future. But anyway, that's how it feels to get old. Sometimes you start not enjoying the changes, some changes, and you think that the past was better. Like oh, C is much better, and has no curly braces. How terrible! But anyway, it should be the same in Python. Well, anyway, in this case, we can clearly differentiate between the first one and the second one, so that the syntax or the grammar of C and Java and probably Python is not ambiguous. For this language, for this part, our grammar is ambiguous because we have two different parses with different meanings for the same sentence, for the same string in this case. This is an ambiguous grammar, and this was what the homework was about. Show that the grammar is ambiguous by showing that the string ictic says has derivation derivations that produce different parse trees. And with this, you can check the difference between leftmost derivation and rightmost derivation, because it does not depend on if we start derivating this string from the left or from the right. Anyway, we can have different choices and we will have different results. Yes. So ambiguous is when we have different parse trees, and leftmost derivation is when we start changing symbols from the left and then from the right. Okay, 100% understood, or 58% understood, or 20% understood?
So it doesn't matter if we start with on the right or on the left. The problem is when it makes different derivations.
Right. When you are able to make different derivations, then it means the grammar is ambiguous. The ambiguity is inherent to the grammar, because this grammar is ambiguous.
Okay.
You can choose to group this part, or you can choose to group this part. It depends on how you choose the order of the rules. In this case, what is affecting is the order of the rules, not the order of the parsing. Yes?
Okay.
Okay, now with this a little bit more clear, we will see two different mechanisms to obtain different derivations depending on how we implement it. You remember, let me go back. Oh, sorry. There was here. I see. The thing that is behind here. So you cannot see it anymore. I will draw it again. So this is how to obtain a push-down automaton from a grammar. And we saw very quickly last time, on the last 5 minutes, it was very quick, so we will see it again with more time today. We saw that it was pretty easy to obtain a push-down automaton from a context-free grammar. And that's very good. Now, I will show you that there are two different ways of doing this. The two of them are quite easy, but we have different results. So the first one consists as before. Let me try to copy a drawing so that we don't have to draw it again. Give me 1 minute. Okay. So for the same grammar, I told you we will end up knowing it by heart. A, M, A, B, and Z, and Z. So this is our old friend. Now I'll try to copy this. Here it is. So you can see several things here. First, that we are inserting the hash into the stack, then we are inserting an S, and then all the operation is in the stack. So we have not seen yet how this is working, so let's do it right now. What happens if we want to analyze the string Zaza? Let me make this a little bit bigger. What happens? Well, we have our string Zaza, and we have our stack here. And we will assume it's empty. As we said before, maybe there is a lot of garbage here. So we don't care, but we will start in this point. So we start by adding this, this hashtag or hash. And now we have moved from this state to this state. Remember, these lambdas mean that we will ignore the input and we will ignore the top of the stack. We will just insert a hash into the stack. Remember as well, our reading head is here. This is the head of the machine on the tape, and this is reading a Z that we have not consumed because we have just ignored it. Then the second state says, again, ignore the input, ignore the top of the stack, and insert an S on top of the stack. So we will have this, an S. Now, please note that we are inserting uppercase symbols onto the stack. Why? Because remember that our symbols of the stack can be different from those of the language we are trying to accept. So in this case, our stack symbols are hash, S, M, N, and of course, A, B, and Z. These are the symbols of our stack, while the symbols for our language are only A, B, and C. Remember that we have different symbol sets for our push-down automaton. Okay, so we put onto the stack, we push onto the stack and S. Now we are here. Last time we drew this state like quite big because we have, as you can see, a lot of arcs coming out of it and into it. Remember that this was constructed by simply observing each one of the rules, S, Z, M, and Z, and practically this is the same rule, S and insert Z, M, and Z. So for each grammar rule, you will just take out or pop the stack symbol at the left and push the rightmost part of the rule. You can see as well several symbols here. And this is the only time you will see this when we are converting this. It means that it will gradually insert each one of these states, starting from right to left, meaning that we will have something like Z, N, M, Z. Yes. So when we insert this into the stack, it will be in this order: first the Z, then the N, then the M, and finally the Z. Or if you want to see it, to read it in order, you will have from left to right and then from top to down. But I think it's better to think on the red arrow because you are taking each by each, insert it onto the stack. Yes, so it depends on how you visualize it. At the end, your stack should have something like this: Z, M, N, Z, Z, M, N, Z. Okay, so now we are here. We are on Q, and we have several options. When we are at Q, we can, for example, change this Z onto. No, we cannot do anything, I think. Not yet, no. The only thing we can do here is try to convert this S into Z, M, and Z. This is the only thing we can do to follow this arc. Why? Because we have an S at the top of the string and of the top of the stack, and it says pop the S and change it for the M and Z. We cannot follow this one because at the top of the stack there is not an M, at the top of the stack there is not an N, so we cannot follow this or this. And while we have this Z at the beginning of our string, we cannot read it because we would need a Z or a Z at the top of the stack that we don't have. So we cannot follow this arc. The only one we can follow is the blue one. Now that we know this, then we will change it this S. We take it out, we pop it and insert an Z, N, M, Z, as we saw here. Okay, now we have several options now. We can, well, not several, I think the only option that we have now is the green one, because now we have the two conditions. We have at the top of the stack a Z, and we have at the beginning of the string a Z, which is the condition that is asked by that arc. So we will do so. We will consume this, we will move our head, and we will consume this one. Okay, I will erase so that it gets less cluttered. Now the top of my stack is here, and now I am reading this one. When we have this M, however, we have two options. We have the option of taking it out and inserting AMA, or we have the option of taking it out and inserting a Z. So keep an eye, this is not ambiguity in terms of the grammar itself. It's just ambiguity on which one of the rules we should apply. It doesn't mean the grammar is ambiguous, just we don't know which rule to apply. So in this case, as we know that it's better for us to process an AMA, we will follow this one. And now you will ask me, or you should ask me, why we are not, how do we know which one of these rules to apply? Well, first you can see this is a non-deterministic automaton. And as that, you remember also that when we have several options, in theory, we should be able to explore all of them. And if there is one of those options or of those paths that leads us to an acceptable string, then it means the string is acceptable. So computationally, also you can see that this can be very complex because we can have a lot of alternatives and we need to explore each one of them, and it can grow exponentially, meaning that parsing a very complex string with a complex grammar could take very long time. For this, we will see next some strategies to optimize this. Okay, so in the meanwhile, in the meantime, we have this and this. We know we have this, so we will use the left one, this one. By using that one, then it says take out the M and insert AMA. Now, we are still here. Our second step will take this A and consume this one and this one. Consume the A from the input, move our head, and consume the A from the top of the stack because we are using this rule. And it says consume the A from the input string, consume the A from the stack, and do not push anything. Now we have this Z at the top and this M. If we erase to make it less cluttered, we can see this. So we have this Z and this M. Follow this rule, this R here, saying that we need to take out the M and change it for a Z. And please note again that we could again change this M for AMA. Again, we have the choice of this or this. How do we know? Well, we know that we should use this one because otherwise we won't obtain we won't get to S. However, in very complex grammar, we do not know this, so we should explore all the possibilities. And this can be cumbersome and computationally expensive. Well, in this case, so we consume this Z. No. we change this, sorry, we change this M for Z. Okay, now I can consume this Z and consume this one and move our head like this. Now, also we can consume this A and this A because we can follow this rule. Let's do that. Consume this A, move our head, and consume this A. Now we have an N. And we have our final choice of rules. We can choose the first one or the second one. And again, we know in this case, if we do B and B, it will be better because we need a B afterwards. But that's what we know. The machine does not know anything. The machine needs to explore, because it's a theoretical machine, the machine should explore all different possibilities. Okay, so we will change this N into B and B. And now we are able to consume this B and, oh my God, sorry. Okay, and now we can follow this second rule, this, and we will change this N for B and B. I think we did this already, but with the interruption, we need to change again, sorry. Okay, so now I can consume this B, and now we have this N. And now we need to use this rule, B, to consume it. This is what we did here. Now we have this N, we will change it for Z. And I think now you know we will just finish Z, B, Z, and we have Z, B, Z here. So we will read our Z, read this B, and consume it from the stack, read this Z, and consume it from the stack. And finally, to change into an accept state, we need to take out the hash from the stack, which means erasing this. And we have reached both conditions of an accept state and okay, I'm back. So I'm still alive. So how are you? Have you got this without trouble? I think it's pretty easy. Maybe it's a bit, well, I think you can get it with no problem, right?
I have only a question.
Please.
What's the reason that, for example, in the letter M, the machine chooses the state or the loop lambda M AMM first to the other accept state, the other loop, sorry.
Like this one, right?
Yes,
so
yes,
you
yes.
Why do we follow this one instead of following this one? Well, remember, the machine is not choosing, we are choosing. The machine says follow either this or this. So there is another execution that we did not see here there is another execution in theory that uses actually this one, but at the end, after many evaluations, it does not reach the accept state. So we need to follow all of them. So maybe we can quickly do that. And if we have Z, A, Z, A, B, Z, B, Z. So let's try to do this a little bit quick. We start with the hash and then S, we are reading this. And we change this ZMN Z, which is not ambiguous. It's the only possibility. So we change S for ZMNZ. And then at this point, we have only the possibility of reading this one, moving our head, and consuming this one. Now we get to the point that Emilio is asking. We followed this one. What if we choose to follow the second one? Then it means we would change this M onto Z, right? And it's possible. It's possible. The machine is not choosing at this point, and that's a very good question, because the next subject here will be how to be able to choose. But in this case, the machine does not know. So we get this Z. In order to consume this Z, we need a rule that has here a Z and here a Z. We do not have that. Then it won't be possible to consume this A. And there are no other rules that deal with a Z at the top of the stack. So after this one, we cannot continue processing the string. Then what usually a program does is a back tracing. It goes back to the last choice it had to do. Then the first choice was not good, then it has to reset its state. It was M, and then change its opinion. Now we need to change M into AMA. AMA, and now we are able to get rid of this A because we have an A here and we have this rule. Yes, Emilio?
Okay. So I will say that the machine prove these loops. Yeah.
Yeah, it tries to explore each one of these loops. It tries all of them. It explores all of them. It has to do that. So in the first example, maybe we did not do it explicitly, but in theory, the machine tries to see everything.
Okay. So thanks.
Welcome, Emilio. So that's a very good question, because as I told you before, this is one of the main problems of these kind of machines, that we don't know how to decide. And this is solved by introducing a very simple mechanism. This is called LL1. So this mechanism, or this way of helping the machine, consists on adding a table, an LL1 table. It will be 1 because it helps us by having a look ahead. This one corresponds to the look ahead. And with this, we will be able to take a decision on what rule we should choose, avoiding successfully, for this grammar, avoiding having to explore possibilities. But I insist, for this grammar, we will see now some limitations. So let me show you the LL table. I'm looking for it to copy. So now our parser can be written as this way. Let me erase here. This is a pseudocode that looks a little bit as Pascal, and it handles the stack. Is it visible or is it too small? Let me make the table smaller and the code a little bit bigger. Okay, there it is. So this code is similar to what we are doing here. It's similar because it's not equivalent. So don't think it's exactly the same. It's very similar. Why it's not similar? Why it's not exactly the same? We will see. So first push and S is this part, push and S. Then read symbol. Read symbol means read from the input string. So it means read this one, read symbol. While the stack is not empty, in this case, we are assuming the stack is empty. Depending on what's on the top of the stack, if this is a symbol, then pop stack and read symbol. It means that if the top of the stack, well, we don't have in this case a hash, but if we have something like a Z, something like this, if we have this, then we can read the symbol, read symbol, and pop stack. Take out this one. So by this instruction, pop stack and read symbol, we are executing all these instructions here. This is equivalent to pop stack and read symbol. If we have something that is different, for example, that we want to read an A and it's not the same A and A here, then exit to error routine, meaning error. This is if in the case that the top of the stack is a symbol. If it is not a symbol, then it is a non-terminal, the top of the stack. So in this case, we have a symbol, meaning that we do this. We read this and pop the stack. Now, for the second case, we have a non-terminal, an M, and then we will consult this table. If the top of the stack and symbol, it means the top of the stack is an M, and the symbol is here, then we have to look up for M and A, M and A. Then replace top of the stack with table, meaning take out this M and change for AMA, meaning that we can just pop it out and change AAMA. And now loop again. If we loop again, then we have top of the stack is symbol, yes. Then pop stack and read symbol, same. Then we have to pop this and move and pop this, we have this. And now we have again non-terminal. We have to look top of the stack and the symbol. Stack and the symbol, but now symbol is Z. So now we have to change M for Z by looking at this part of the table. So it means that we can just change this M for Z. So maybe we will not do that again because you can get bored if we keep doing this for this table. But I want to stop at this point. Why? Because as you saw, by means of this table and looking ahead one symbol, we are able to choose the correct rule. This represents the rule with AMA. This represents this rule. And the other one represents the rule with Z. M goes to Z. And the same for the other ones. We have BNB, is this rule, and we have also n gets to z is this rule. And finally, of course, the other rules, this one is this rule. So to get rid of this complexity for this grammar is pretty easy. Why? Because only by looking ahead one symbol, we can know which one, we are able to know which one of the rules we need to apply. And that's easy and kind of evident, because if we focus on this part, we can see that the ambiguity or maybe not the ambiguity, but the question on which one of the rules we should apply, being this or this, can be solved just by looking the first one of the symbols. If we look for this A, we know that we need to apply this rule. If we see this Z, then we know that we have to apply this rule. So by this means, it's much more easy to work for this grammar. This is an LL1 parser. Now I will show you a parser that cannot be, or a grammar that cannot work with this kind of parsers. Okay, so far, is this clear? Okay, now let me show you a grammar that does not work with an LL1 parser. We have something like this, X, Y, T, Y, Z, and then we have this. In order to, you can see there is ambiguity here, so, because we don't know, given an X, if we have to apply this rule or this rule. So what can we do? We need to expand this first rule in order to have the possibilities. So this will expand into two rules. Why two? Because S has two different options. So we will substitute S with the first option, and we will substitute the same S with the second option. If we substitute with the first option, we will have S, X, X, S, Z, Z. Yes, because we are substituting X, S, Z with this part. The second option will be X, X, Y, T, Y, Z, Z. Yeah, thank you. Because this will be the second part of it. And these two represent the first rule, meaning that if we look XX, we need to apply the first rule. The second one is not, we don't need to expand it. And we know that for the second one, if we see XY, then we need to apply the second rule. However, I want you to notice that if we look only one symbol ahead, the X, we do not know. We need to look ahead two symbols, meaning that this grammar needs an LL2. It looks like a Z, an LL2 parser. And the table for this one would look as this. If we have X and we have XX, we need to apply the first rule, XSZ. And if we see XY, we need to apply the second rule. And that's it. If we have a T, we do not, we just can substitute for nothing. And of course, we should explore other options like YX, YY, and X end of string, and Y end of string. In any of these cases would be error. So this would be the table of LL2. So please note that we needed to see two characters ahead in order to disambiguate which rule we should apply. But then it is possible to use an LL parser in order to know which one we need to apply. So far, we are creating, or we are exploring, the LLK parsers, which are a subset of the context-free grammars regarding the languages they accept. Why? Because not all grammars can be parsed by an LLK parser. There are some grammars that are not suitable for accepting this, for accepting a context-free grammar. For example, imagine you have a language that says X n times, with n belonging to the natural numbers, and xn, yn. So this language would consist of strings going from lambda to x or xy, xx, xxyy, xxx, xxxyyyy, etc. This language, I want you to show me first the grammar for this language. So before we keep on going, please write on your notebooks the grammar corresponding to this language L. So probably you are trying to do first the grammar rules for this one, and then the grammar rules for this one. Then you need just to make the union of both grammars, which is not just adding all rules, but selecting one set or another set. But then you can try first this sublanguage and then this sublanguage. Now you have a mini quiz on screen so that you need to choose the correct set of rules. Or not the correct set, but each one of the rules that compose this grammar. So you need to choose all the rules that belong to this language, to the world language. Okay, time over. So please cast your votes, whatever they are. Please go ahead. Let's see if we can all together solve this conundrum. So far, we have 2 people out of 17 that has voted. So I want all of you to vote, even if you are wrong, but please do vote. Otherwise, I will think you are not here, because also I cannot see you. So I want to see your votes at least. So the answer has 1, 2, 3, 4, 5, 6 rules out of these ones. So you must check 6. And to give you another hint, those corresponding to the A part have to do with the A part is this one. A. And the B part is this one. So maybe with this it's clearer, because with the A part we are recognizing for each X we need a Y, exactly 1. And for the other part, for the B part, it says we just need a certain number of X. Okay, closing poll in 1 minute.
Can we change our answers?
I think that if you have submitted, I'm afraid it's not possible.
I had 7, now I have 6.
Okay, well, I'm afraid you cannot change now.
Pressure? Yep, to press?
Yeah.
Oh, pressure? Press. I don't remember.
I want to see your vote.
How many votes are pending?
Well, you should vote for, I don't know, 6 or 7 rules approximately, but I don't see you voting, so I'm worried. So anyway, don't worry. Maybe we can just go ahead and explain this. Okay. Okay. So maybe it was too much pressure for this exercise. Don't worry, because it's something. It's always something new, and sometimes if we feel pressed about something new, just I'm worried because I see I see a lot of people with their cameras turned off, so I don't know if they are following the class or just. Okay, I see you, Sarah. Thank you very much. I'm happy to see you here and all of you. So, well, I just want to make sure you are following the class, because then sometimes we do some questions and we are not sure if you are attending or not with this. Well, at least I can see you. Hello, Oscar. Nice to see you all. So I understand that maybe it's hard to have all the time your camera turned on, but at least sometimes try to turn it on so that I know that you are here. Okay, so let's see what grammars are here. The A part, as the answer said, well, the B part is easier. So let's do that first. Hello, Miguel. Nice to see you. Okay, so we have B, and B says, supposing we want to recognize it. Okay, let's do it separately. Xn should be S and then accept any number of X and then an S again, or S can get to lambda. This is for Xn. And for Xn, Yn, we have this one, X, X, Y, and then S can go to lambda. So independently, for each one of the grammars, hello, Erika, we have this for the xn, x times, meaning that we can just continue. Hello, Heriberto. We can, and hello, Cesar. We have a lot of times x repeated, and meaning that we have the option of keeping with the repetition of s, or we can just stop at any time, at any moment with the lambda. And for the second one, we have to insert in the middle here, again, an S, meaning we have an X at the left side and a Y at the right side, or a lambda. So this is the grammar for recognizing this language, and this is the grammar for recognizing this language. Yes. So maybe we hadn't seen this before, so maybe trying to figure it directly, it was a bit complicated. Not that much. Now that you know how to do it, well, it won't be difficult for the next time. Okay, now how to mix them or merge them into a single grammar? Well, first of all, the S of this part should be changed into a different letter. Let's say B, XB, and then B goes to lambda. And the second one will be A. It can be another letter, of course, but we choose to make it A. XAY, and then A goes to lambda. And finally, in order to mix them, to merge them, we need some rules that says S can be A or S can be B. And that's it. And of course, S can be lambda as well. This is a redundant rule because if S can be A in turn can be lambda, and B in turn can be lambda. So we don't need the rule, but if we want to add it, it's very good. Okay, and so the answer would be to tick this, and this. Actually, the lambda one was just a single one with semicolons. Okay, so I hope with this it's clearer. And now we are using this example to show why this not work with an LLK parser. Let me rewrite this grammar into a clean screen. So I will just change and rewrite. We have the following rules. S goes to A or S goes to B. Then A is XS, oh sorry, XA Y or lambda, and B is XB or lambda. That's our rule. 1, 2, 3, 4, 5, 6. I think those were the 6 rules. There were some rules that are not right, were not right in the poll. For example, A, X, S, Y. And this is not correct because it allows us to go back to B. And if we go back to B, then we have a mix between X and XY. So we want only X, X, Y, Y. And we want, on the other side, we want just X or XX or XXX. If we allow them to mix, then we can have perhaps things like, I can repeat as many X as I want, and at the end, we add XY. You see, or maybe we can have different mixes, and we don't want this to be here. So that's why we don't want the S here. We need them to be independent. So from the beginning, we say that with A or B. Okay. So what is the problem when we try to do an LLK parser? Yes, Christian, please.
Yes, Professor, I think we are missing one rule, right? The S goes to lambda.
Oh, yes, I added that before because it was combined, right? It said something like this and this in the poll. And in the previous screen, we said that if we can add that as well. However, this is redundant. Why? Because we can have S goes to A and A goes to lambda. That is equivalent to have S goes to lambda. So we can erase this and the grammar is the same, is equivalent. The language is the same. The grammar is not the same, but the language is the same. Yes, Christian?
Yes, thank you.
Okay. So yes, if we add S goes to lambda, is exactly the same. Thank you. Okay, so for LLK, let's try with an LL1, which means trying to see if we can disambiguate between in this case, A or B, which is our ambiguous or main, the main rules that we need to start from the beginning. So if we focus on this, and if we substitute them, we have for A, we have XAY, or we have lambda. And the second one can be substituted as XB or lambda. We won't care for lambda rules right now because we want to disambiguate with the others. And we can see that if we focus on the first symbol, we cannot disambiguate. Why? Because it's an X in both cases. Okay, so we cannot use an LL1. Let's try with an LL2. Then we expand this again. If we expand A, we have two expansions as well. We have X, X, A, Y, Y, or X, X, Y, substituting by lambda. And this one, we can substitute again with X, XB, or X. And we can see again that we cannot disambiguate because we need to know which set of rules we should choose, this or this. I need to know, should I choose A or B by looking ahead, this one. I can do this with XY with no problem, but we need to have a complete selection, a complete, we need to know for sure which one of the rules we need to use. So again, we have XX and XX. I cannot use an LL2. Let's try an LL3. And again, if we expand this, we will have X, 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 A, Y, 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 or X, X, Y, Y. And in this case, again, if we expand, we will have X, 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 or X, X. Again, we cannot decide with this because it's exactly the same. I forgot the B. It's exactly the same. So we cannot use an LL3. And then you start seeing the reasoning. If we keep doing this, we cannot use an LL4 and we cannot use an LL5, etc. Meaning that we cannot use an LLK for this particular language. So this is a good example of what kind of languages cannot be parsed by using an LLK parser. Why? Because remember that we want to use some look ahead, and maybe we have 10x, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And at this point, we don't know if we will see 10 y's. Maybe yes, maybe not, because this language does not allow us to have a certain number of look aheads in order to know which set of rules do we need. If we had only X, we need to use the B set of rules. If we have the X by 10 Ys, we would need to use the A set of rules. So we don't know, it's not possible. So I want you to show you, I want to show you that this strategy of look ahead is not always possible. So we need some other strategy called the LRK look ahead parsers. And we don't have too much time. Christian has your hand is raised. Is the same hand or is the other hand?
Yes, sir.
Just same hand or just new hand?
No, it was the same hand, sorry.
Okay. So far, is this clear or so?
Oh, it's clear.
Okay, so I hope you are not thinking that, but if it's so, well, maybe we can try to teach it differently. Just try. Okay, so now let's see an LRK parser. Before doing so, do you remember, let me go back. Do you remember I told you there were two different ways of doing this? We have seen the first one. Now let's see the second one before I show you the second, the LR parsers. So again, I will copy paste from our book. Okay, this is it. This is the second way of doing it. And of course, this is designed for the same grammar we have been working on, the Zaza grammar. So let's see how this works. This will have the same problem as before, that we need to do all the different we need to explore all the different possibilities before saying that a grammar can be accepted. or not. So suppose we have Zaza, bzz, bzz. Again. We start here, and there's a mistake here because it doesn't say that we need to introduce the cat, the hash. So this was an error for the Spanish version. Now that I'm using the English one, I see it's the same one. Okay, don't worry. And there's another error here. This S should be capital. Okay. So let's work with Zaza. We start here, and we have also our stack here. The first thing it says is add a hash here. Our head is here, and now we go directly into this big state. So we don't add the S automatically. So we need to obtain it so that at the end we are able to pop it out from the grammar, from the stack. So let's see which options do we have. At any moment that we have a symbol from the input, we can add it to the stack. So we can have, we could try to consume all the symbols, something like this. And we just finish reading this and get to this point. But of course, we cannot get to the final state because we need to consume the hash. So we cannot do that. That's not a good strategy. Little by little, just reading this Z arc, we read this Z and move here. And now we have an A, should we consume it or not? So now our questions are broader. What should I do? Should I consume this symbol, or should I wait for more symbols to come? So let's try in this case to have more symbols. Let's consume this A, and then this Z. And then we need to take a decision, because we know that at some point we need to have AMA. So at this point, we would like to have this Z changed by an M. So magically, we decide to choose this arc now. And I say magically because you will ask, well, why the teacher choose this? Well, just because I take it out from my sleeve, like here. Here is the reason. Well, I do it because I know that this will help us to obtain S at the end. But as before, there is no way the machine knows. There will be a table in the future, and this table will be called LRK parser. Yes, but at this point, we don't know. And we just have to try everything. We won't do it because it would take us a lot of time, but just I want you to make you conscious of this. So we follow this, this green arc, meaning that I pop out the Z and push an M. Pop out the Z and push an M. And now I can keep reading symbols from the input. We take this A here. And now we have this nice AMA that can be popped out in order to push in an M. So let's do that. AMA goes to hell, and then M. Yeah, poor symbols. They went into the hell of symbols, but don't worry, we can just rescue them in the future. Okay, now we have B. We will continue following these arcs of below. So we consume the B, we consume the Z, and again, we know that it will be good for us to change this Z into an N. So we will follow this arc. By doing so, we delete this Z and change it for an N. We continue consuming symbols. And sorry, this, yes, we consume the B. And now we have B and B. B and B that we have here. So we will take out this B and B and change it for an N. And finally, we will consume this Z and see what we have here. We have ZNMZ, which is ZNMZ, meaning that I can take out this and substitute with an S. And we can just consume this S following this arc. And then we can consume the hash. And we have reached both an accept state and the end of string, meaning this string is accepted. So this is the other way this push-down automata can recognize a string. So we have seen two different ways. In one way, we start by consuming symbols only when we have at the top of the stack. In this second way, we can do that only, we can do that whenever we want. As I show in the beginning, maybe at the beginning we could load all string like this, but this won't work because then I cannot convert each one of them. So now the question lies on which part of my automaton should I follow, these arcs or this part of here? At which moment we can change a symbol into an M, or we should change it into an N? How to know? So we will have something very similar to the principle of look ahead, but we will see this on the next class. In the meanwhile, I will leave you some exercises. I hope them to be very simple. So that you have time, because as you told me before, you have a lot of homework. So page 130, please do exercise 1, 2, and number 3, you are not ready yet. Let me see. We will see that on the next class. And page 118, exercise 3 and 4. That's it. So they are not so complicated. And of course, the more complicated ones, we will do them in class next time. So I will, I don't know why I have the sensation you have too many questions. I hope everything is clear. I will try to upload the recording of these procedures so that you have them very, very clear. Yes, and perhaps when you are doing your homework, it will be more and more clear to you. If not, please feel free to ask. Okay? Okay, well. So we have 3 minutes for questions or complaints or else. Sarah.
Will you open both homeworks on Thursday?
Yes, let's do the following. This is for April 29th. And let's keep the second one for Monday, okay? I think you already have it. If you already have it, please upload it. However, I don't want you to.
Because I can see it on Moodle.
Yes, I forgot to open that, so that's why I give you more time. So the previous. I think the previous homework is quite easy. So probably you already have it, but in case you feel you have so many things on your head, well, you can just do it on the weekend or the Friday, or like take some time to synchronize. And the description will be there. I think you'll have clearer idea on what to do about ambiguous grammar or the if condition then sentence else sentence, and that will be for Monday the 3rd, May the 3rd. And this one I want you to do it for April 29th, because in order to keep with the subjects we are studying. Okay. Okay, so thank you very much for your attention. I hope you have a lot of questions, and if that's the case, we will see next Thursday. Take care and see you.
Thank you. Bye.
Thank you, doctor.
See you,
Thank
teacher.
you.
Have a nice day.
Adios.
See you.